so rattled by my technical difficulties earlier. I was like, I understand like the first half of my presentation. It survived. Survived. Just kind of survived. Yeah. And I think that's sorry. Forking is great. Forking is good. You don't need cheese if you don't fork. Your sequence numbers are enough. The sequence numbers are enough. Hey. Oh, to what? Okay.
Can I ask the panelists to please take their seats? Vitalik, Vlad, take your seat. Peter, Goon, yes, please.
Well, where's the mic?
Can you just use this?
Oh, that's pretty far. Can I have another handheld mic? Okay, all right. Hello. Okay, and we are moving on to the panel, and this panel is about Casper and distributed consensus. My name is ゚D㚚щ. I'm a professor at Cornell, and I'm very honored to moderate this panel. We have 4 distinguished panelists, and I'm going to begin by having the panelists each spend 2 minutes to introduce, and also maybe a short, concise statement or pitch that you would like to make regarding distributed consensus. And then I'm going to ask questions, and I'm going to open it up for the audience to ask questions. So because we have a big room, for those of you who want to ask questions, I'm going to ask you to move to the front so everyone can hear you when you ask questions. Okay, all right. Let's maybe start from Vitalik. Okay.
Hello everyone. Who here does not know my name? Okay, I see some hands raised. Good. I'm Vitalik, Chief Scientist of the Ethereum Foundation. So earlier this morning, I gave an introduction to basically what Ethereum is from a technical standpoint, but I also mentioned that later today I'd be talking a bit more about some of the projected things that we want to do in the future of Ethereum. And one of the big threads kind of research and developments that we have at the Ethereum Foundation is Casper. So Casper is this kind of category of proof-of-stake consensus protocols that we have been thinking about and developing, researching over the last few years that are kind of based around a couple of principles, right? So one of them is obviously decentralization and Byzantine fault tolerance, which is really a synonym for decentralization because both words basically mean that one single guy can't screw up and break the whole thing. Then we also have this idea of economic security that I'm sure Vlad will talk about much more, and you can really credit him for kind of pushing hard on putting that at the front of the agenda. So personally, I have been spending my time more specifically on pushing forward with Casper, the friendly finality gadget, or a Casper FFG. So this is one of the 2 kind of algorithms in the Casper family, and the goal of Casper FFG is to be something that's as simple as possible and as simple to graft onto the existing proof-of-work chains as possible, while at the same time theoretically being a fully fledged and provably safe under asynchrony Byzantine fault-tolerant consensus algorithm. So the idea is that it takes sort of PBFT Lamport's Byzantine generalist paper-like ideas and basically translates them into a blockchain context and really simplifies them substantially to the point where, as Chang-Woo showed earlier today, the kind of consensus rules, slashing addition, fortress rules are fairly simple to implement. So the goal of Casper FFG is to basically be proof of stake that can be implemented fairly quickly, overlaid onto any proof of work chain today, with an eye to, in later stages of the roadmap, implementing more advanced things like full proof of stake, so getting rid of the proof of work completely, as well as things like some of the more advanced features that Vlad wants to include.
Yeah, thanks for talk. Yeah, so I mean, I definitely feel like the proof of stake research that we've been doing over the years has two kind of bifurcations, like the economic stuff and the consensus stuff, and they're really kind of at the end of the day end up being really tightly connected, because the limit to our ability to incentivize the nodes is to infer what behavior they actually did, and the limits there are actually limits to fault attribution, and that has to do with really the mechanics of the protocol, right? Which is why we want not just to say prove that it's fault tolerant, but prove that when there are faults, we can find them, right? So that we can penalize the faulty nodes, so that not only can we tolerate faults, but we also disincentivize them. So, and I think that both sides of the research have kind of come a long way and actually feed into each other actually in a very kind of tight way. To me, today, the thing that's the most exciting to me is kind of the stuff that I kind of just showed, right? I like the fact that I think we can get, I'm sure we can get asynchronous safety with any, just pick your fault tolerance threshold with an overhead of Nakamoto consensus is, I think, really cool, and something that, is, I think, new technology. And I kind of want to echo what Vitalik said, that I think the simplicity of the protocol specification and the simplicity of the proofs is kind of paramount to our design philosophy or our design goal.
Hello, I am Peter from Parity Technologies. So at Parity, we've been implementing, we've been working on on implementation in particular of consensus for a while. And we kind of taken a step-by-step approach. Now it's somewhat converging to a lot of research that is coming out. But we started by separating the validator set. So the piece that decides who is the current set of validators. So when it might be determined by their stake or by support of other parties. So that would be proof of authority. And then the consensus algorithm itself. And then we started off with a very kind of simple consensus algorithm that was based on on basically issuing proposals in a round. It is somewhat similar to what Vlad talked about at the end, where validators kind of issue blocks sequentially. And then we added finality, so that was basically a module that then looks at the blockchain at any particular point and sees who signed off on which chain, and basically if someone signed off on a chain, then that contributes to finalizing that particular chain. And now I think the other things that will be interesting is introducing new message types, so enabling not only validators to finalize blocks not only by releasing blocks, but also releasing just simply statements of validity of a particular chain, speeding up how fast the blocks can be finalized in these types of algorithms. And of course, working more on the validator set, so working more on the economic side of those protocols. And yeah, the validator set as are right now, they support providing misbehavior proofs, and those misbehavior proofs can depend on the type of consensus engine, so they might be double signing, and then the verification of the misbehavior proof happens on chain, and then slashing can be done based on that.
Okay, well, thank you very much for having me here. My name is Emin Günsirer. I'm a professor at Cornell University. I'm also a co-director at the Initiative for Cryptocurrencies and Smart Contracts. So there are a couple of things that people should maybe know about me, but the most important one, beyond anything I've done in the past, like I did play a pretty early role in cryptocurrencies in something called Karma in 2002, 2003. It was one of the first implemented system with a proof of work minting in it. But beyond that, many of you know that I played a role in anticipating the DAO hack and so forth. But the most important thing, I think, is the following. It's I think, partly why I'm so excited to be here. This is a very science-driven community, and in much of my work, what I really value is science-based design with strong guarantees. So this is a domain where there are many reasonable-sounding protocols that anybody could just come up with at any one time. I essentially reach into my gut and I give you something. Oh, A sends a message to B, sends a message to C, then this happens and that happens. And there's been no shortage of white papers containing these kinds of what we call design by gut, or wishful thinking design, or sunny day design. And those are fine, they might work. But as we often find out, the devil is in the details, and what you should all demand as a community are actual hard proofs. In the absence of those proofs, these systems typically tend to falter. So in every answer that I give to any question is colored by the science-driven design. I'm very much restricted in what I can say publicly and privately, because I have to just say things that I know to be true. That has allowed me to actually be very correct and prescient in some ways, but it also means that I demand a higher bar for protocol design. And I hope you will too. And I think what we're seeing happen is Casper is gradually getting to the point where it's actually beginning to reach that bar. And we're finally getting to the point where we understand the workings of the protocol better. And we will hopefully soon have something ready to roll out.
Okay, well, thank you so much for the excellent statements. And I'm going to begin by asking a couple of questions. And if you would like to ask a question, I'm going to ask you to maybe move to the front and at the yellow line. And then Ming will be able to pass you the mic. Okay, so my first question is regarding the debate between proof of work and proof of stake, right? So we all know proof of work is probably in the longer term not what we want because of the enormous energy waste. But there have been a lot of debates in the community about the security of proof of work versus the security of proof of stake. Some argue proof of work is more secure, others argue proof of stake is more secure. So for Ethereum, for instance, one reason why you guys are moving to proof of stake, I mean, obviously, other than the energy waste, you also want to have an incentive-compatible protocol. But I wonder what you guys think of this question, like the security of proof of work versus proof of stake. In particular, imagine I'm not a rational player. I just want to attack the system and break the consistency. Do you think like the proof of stake approach actually increases the cost of such an attack?
Start?
Yeah, sure, I would love to. So firstly, I would say okay, proof of work is not asynchronously safe, right? And it's one of the main differences actually between proof of stake and proof of work is that in proof of stake you can actually achieve finality, right? And actually decisions that are not going to be reverted and that are safe in asynchrony. I think that increases the security a lot. And I think that in terms of the damage that an attack could do, the fact that blocks can't be reverted arbitrarily really mitigates that. And then additionally, the fact that when the safety failure does happen, the faults are attributable and the nodes who attack can lose money, means that the nodes who are attacking will operate at a higher cost than nodes who are not attacking, which is not the case in proof of work. So I think, for those reasons and more, proof of stake is going to be more expensive to attack, and your attacks are going to be more limited.
Yeah, so let's say that you are, just to be politically neutral, the government of the Democratic People's Republic of Korea, and you want to basically destroy a proof of work blockchain, right? So what do? Step one, we could just imagine a very full direct attack, right? So you would get $1 billion, and okay, fine, some of your people can go without food, but you get $1 billion, and you buy a whole bunch of ASICs, and then you just launch a 51% attack on the network. Now, what are the developers going to do in response? Well, they have exactly one strategy, which is change the proof of work algorithm. So let's say they do that, right? So what happens? This is basically kind of literally the best possible counter move, because if you don't do that, then they can do what's called a spawn camp attack, which is basically they just keep on attacking over and over again and they make your chain permanently useless. So you change the proof of work algorithm, which means the ASICs become useless, which means that the attacker has lost $1 billion, but all of the good guy miners lost all of their money as well. Right, so that's one area where proof of work already starts to show weakness, because it means that if an attack is going to happen, then there's actually fairly little incentive to be on the non-attacking side versus being on the attacking side. So then, okay, it's down to GPUs. Now let's say you get another $1 billion and you basically corner the market on GPUs. Well, okay, you launch another 51% attack, or general purpose hardware. And so the developers have no other counter move, right? Basically step 3 of the game, and that's game over. They can just do, this North Korean government could just keep on doing a spawn camping, can keep on just censoring transactions, doing 51% attacks. You cannot change the proof of work algorithm again, because if you change it again, then, well, for the new algorithm, GPUs are going to work for it as well. So this kind of puts an upper bound on basically the amount of damage that a proof of work chain can take, which basically means that a proof of work chain has, in order to survive, has to make this cost of attack very high, which is basically this kind of doctrine of survival through domination and massive hash power. Now let's look at proof of stake. Okay, so Uncle Kim buys up $100 million of Ether. Then okay, fine. BFT 34% bounds, so you can definitely launch a 34% attack or a 51% attack. So okay, you launch an attack, and let's say this breaks finality or this censors transactions for a while. Well, guess what? The economics of Casper are designed in such a way that if you do this, then worst comes to worst, the community can coordinate a hard fork. So this is a totally legitimate move, because even the proof of work people agree that changing the proof of work is a legitimate move to counter a 51% attack, and that's also a hard fork. So the community does a hard fork to hard fork away from the attack. Now the difference here is, first of all, the attacker actually does lose most or all of the money they used to attack, and second, anyone who did not participate in the attack does not lose any money. So okay, step 2 of the game. Basically, 3 days of chaos happen, the community recovers, there's a hard fork. Well, okay, buy up another $100 million, do another attack. Okay, 3 days of chaos, community recovers. Buy up another $100 million of Ether. Well, soon enough, the community is going to realize that this is what's happening. Eventually, Uncle Kim is going to run out of money, and so they're just going to sit quietly, and people are going to start buying up Ether, and each and every one of these attacks is going to keep increasing the price of Ether, because it's basically taking $100 million of Ether off the market each time and permanently destroying it. So eventually you run out of money and the community wins. Right? So this is basically the moral of the story is that because in proof of stake, the staking coins are defined or the assets used to stake are defined inside the system. The result basically is that you can make these rules, that you have a huge amount of flexibility to make these rules that are basically extremely lopsided in the defender's favor. And that basically means that if the attacker has some amount of money, then they can basically break the system maximum a limited amount of times. Now, one really nice goal for this is, of course, to see if we can actually formally prove, the bound on amount of money you have divided by the number of times you can force the community to hard fork, which would by itself be a very interesting challenge, but at least that by itself shows the asymmetry.
So to pile on both Vlad and Vitalik's responses, I think what's going on here is fairly straightforward. With proof of work, we're at the mercy of hardware trends. That's it. The control of the security of the system is out of our hands. As trends change, as people invent new technologies with, let's say, various process level tricks to pack more transistors, to pack better hashers into the same die area, as people come up with better heat, cooling, etc. tricks, we're going to see hash power shift hands, and we will have absolutely nothing in our hands, no knobs we can twist to control what happens. I think everything that you heard from Vitalik was exactly fundamentally rooted at that cause. And with proof of stake, we have the ability to actually put independent individual knobs on each and every one of the participants in the system. This is huge. It gives us an additional multiple levels, multiple dimensions of control over the system. It also makes the problem much more difficult. That's why there were multiple Casper variants. That's why it's actually hard to figure out exactly what you should do because the design space is so big. And so if you could conquer the design challenge, if you could come up with a protocol whose properties you can prove, then the potential for having a secure protocol is much higher for proof of stake than for proof of work.
Yeah, I think, as was mentioned previously, with proof of stake, the distribution of control and of stakers can be much wider. So anyone that has any sort of use of the network can submit a stake and in a way be invested in the security of the network. And there's much less stake in the network rather than having to buy a miner and mine on the network or buying a share in a mining company. It's a much more direct connection to the protocol itself. But then at the same time, I think another problem that can arise is if we have many participants in the consensus, it becomes very expensive to run the consensus process amongst many participants. So a lot of systems have something like a delegated proof of stake where only a few parties actually participate in consensus while everyone is kind of just delegating to someone else. And that can potentially lead to issues with very few parties kind of having a lot of control over the network. So I think an important thing that we'll need to think about is how to kind of manage this balance between distributing the power to every single person that wants to have it and maintaining security or being able to run this consensus in an efficient way.
Just a really quick add-on. Even if the concentration of proof of work and proof of stake were the same, the fact that there's lower barriers to entry in proof of stake will mean that it behaves in a more competitive way. So even though I totally agree, I think like stake is going to be less concentrated than work, it's going to be more competitive even if it's the same concentration. And
because of the liquidity.
Because of the lower barriers to entry.
Yeah, lower barriers.
Yes, I really liked your points. And let's take a question from the audience.
Is there concern? Oh, cool. Is there concern for link rot with a Casper implementation?
What do you mean by link rot?
Yeah,
link rot, like something maybe is staked and placed in the chain, and validated and placed in the chain, but the chain that it's representing is no longer exists after some time.
Do you mean by exist? Do you mean can no longer be downloaded, or do you mean
right? Yeah. Like some of the people who were part of this chain that was then used to be placed in the main chain that doesn't exist anymore, or the users go offline.
So you seem like you're describing a scheme that involves multiple chains. So is this like a question about sharding, or?
Yeah, I think so.
Yeah. Okay. Just to kind of fast forward ahead about 1 hour before we rewind back to here. I guess the answer is that there definitely are in general worries that if the system gets sharded to the point where a very small number of nodes end up like storing each individual piece of data, then it is totally possible that some portions of the state could just end up getting lost. Now, there are ways to make the protocol more capable of surviving that, and there are also ways of mitigating that, and there are also incentivizing storage, and you could also just basically limit the sharding coefficients so that you still have, like statistically speaking, like a few hundred people storing each piece of data so that it's safe enough, and this is a very active area of research.
Thank you.
Okay, we can take maybe one more question from the audience, and hopefully I get to ask my last question.
Okay, here's a question sort of on the economic mechanics between proof of work and proof of stake. So I mean, obviously, right now, proof of work in Bitcoin, for example, or Ethereum, is useless outside of Bitcoin and Ethereum. I mean, you're just doing a bunch of hashes or computing a hash with a DAG. But say if you had a proof of work like, if you could somehow construct a proof of work that wasn't pre-mineable, that solved an interesting problem like protein folding or traveling salesman, then I think with proof of work you have this nicer benefit that you kind of lose in proof of stake, that you can say, look, here we have Moore's law and maximum processing power, the maximum manufacturing capacity in the world, and say, in the next year, only grow up to this point, right? And if the hash rate grows beyond that point, then if the price remains the same, and if the hash rate is beyond that point, it means that the growth of the hash chain's power has exceeded the Moore's law curve, so there has been more economic interest in the chain, and you can have a total upper bound, if 100% of all new processors end up being used for the proof of work. Obviously, you can't have that because that makes the rest of society invaluable, and therefore, there's a good balance there. There's there's a parity balance there that you can compute. And in proof of stake, this isn't the case because, the proof is say that we have 10% of Ether can be staked at any one time or something like that. The security of the chain from one moment to the other really depends on the chain's total value over the ratio of that over world's purchasing power parity, right? The world GDP. So if the world GDP is way high and the chain becomes much more valuable, then because it's the price is really a lagging indicator of that. Somebody could come in and end up having a 51% attack on the chain or have disproportionate stake in the chain because it would be valuable for them. And if they do, either way, also if they do buy a lot of stake to do a 51% attack, they could short, right before they do the attack, which makes it cheaper or perhaps worthwhile. So how do you sort of balance, how do you see, doing the mechanism design so that you balance these incentives, people can't, you make it hard, expensive to short right before you do an attack, and keep more predictable bounds on the amount of how the consensus behavior can change from one moment to the next.
So let me tackle the first part of this question, which had to do with useful proofs of work. So that's an idea that comes up over and over again. I've seen it in many different forms. So first of all, coin designers of different kinds typically shun this idea for a very simple reason. The main reason they cite is if it was the case that minting Bitcoin corresponded to doing 50,000 protein folds, and we know the current cost of doing one protein fold on Amazon, Turk, or whatever, that would anchor the price of a Bitcoin. And people don't want that. They want it to go to the moon. And if it is the case that a protein fold is 5 cents, then you're stuck with a Bitcoin price being 5 times 50,000, 5 cents times 50,000, at least in people's minds. And that would create some kind of a price barrier. So you see coin designers shunning this idea. In response, academics have looked at this and they've come up with different ideas for using useful proofs of useful work. Using things like secure hardware to show that this person actually dedicated their CPU to doing something of importance to themselves, and it's up to you what that was. And there's some interesting work coming out of academia on that front. So that maybe goes towards addressing that issue. The second part of your question, I think, had to do with what happens when somebody is shorting and attacking. And analyzing those kinds of situations is always difficult. But what can one do, right? Essentially, we can reason about coins in the system, and we can model the amount of damage one can do to the external value of the coin as well. And we haven't seen much analysis of that kind, but I hope that moving forward, we will see people take that into account. Because the coins, their number doesn't matter. What matters is the external market value.
And in terms of shorting, if the value is going away completely, then you will not be able to close your short anyways. But in terms of purchasing power, this is something that in general grows, and we could argue that it might be growing at a similar pace to advances in computing hardware.
Okay, let's take one more question from the audience.
Okay, just a quick question about economic finality. I mean, you mentioned that an attacker might buy coins, might Ether and launch an attack, and then the community might realize it did an attack and slash him and hard fork and so on. But do you think that commitment to attack, I send attack the first step, I redo my attack, I do it again, I do it again, I do it again. Some commitment to attack might be community destroying, and also might, for example, incentivize people to sell their coin and leave the protocol?
Well, no, because like as I said, basically I believe that if we can make Casper work well enough, then attacks will make the Ether price go up. And so a commitment to attack will incentivize people to buy. That basically, in my view, is kind of the sort of crypto economic holy grail.
I mean, I agree with V here. I think actually the question you're asking is, if someone commits hard enough to attacking it, can they demoralize everyone and have them no longer believe the story that we will just sell the coins to the attacker at higher and higher prices, right? And the question, like whether people will be demoralized or not, is kind of really about, you know, their kind of states of knowledge and confidence in the kind of belief that you can't conduct this attack, you know, over and over again if it costs you like a significant amount every time. And I think if people really believe that, then it shouldn't make you lose confidence. You should know that, okay, this is only gonna happen a finite and small number of times, and therefore you won't just dump your coins in response of this fear of a persistent attack. So basically, you know, can someone commit to attacking the protocol and therefore demoralize the Ethereum community to the point where the price goes so low that like the security goes to zero? I mean, in theory, but I don't think it's very likely.
Okay, we have time for one last question.
Hey, my understanding with Casper is that if I have been offline for a while and then I come back online, I need the Genesis block, a fork choice rule, and the current validator set. So I was wondering if you could talk a bit about sort of the attack surface of that validator set being subjective, and if there's ways to mitigate that with Casper when we switch over.
But you only have 55 seconds.
Yeah, you don't use the Genesis block, you use something more recent.
Yeah, like the idea is, right, that there is this kind of like a withdrawal revert limit, and so like there might be some period, like say 4 months, and as long as you log in within that period of time, then you would authenticate the current state based on the information that you know, given the previous state that you were aware of at the last time when you logged off. So if you log off for a too long period of time, then like it does become possible to make attacks where those attacks are not paid, like where those attacks can happen without the attacker paying penalties. But if you log on more frequently, then that does not happen.
Okay, all right. So let's thank the panelists for an excellent panel, and thank you very much for your participation.
Thank you very much. Our next speaker is Jason Teutsch, introducing the TrueBit virtual machine. Thank you, panelists.
Okay, Jason. That was great. That was great.
waiting for the mic to come on. Sounds like it's on.
Is he ready? Jason?
Are we ready?
Yes, you're ready. Go ahead.
Could we get the slides up on the screen? Oh, there we go. All right, we're ready. Thanks, everyone. So I'm Jason Teutsch, and we talk about TrueBit. So in what sense am I introducing the TrueBit virtual machine? So some of you remember last year at Devcon3, Christian Reitwiessner also gave a talk on TrueBit. So I'm pleased to announce here today that TrueBit is up on the Kovan testnet. You can take a piece of C or C++ code and run a verification game up there. All the code is up on our GitHub. It's all open source, so dig right in. And I'd also like to thank all of our, in addition to our core team, all of our open source contributors who have been making that into a reality. We are especially Sina Bibian and Harley Swick. So some of you may be old enough to remember, before Bitcoin, there was a thing called big data. And you could actually store stuff on your computer. You could use the computer to compute stuff. And there was even some privacy features. Well, Ethereum sacrificed all these for a property we called immutability. And that's what makes blockchains amazing. They're immutable. They have some sort of democratic equality properties to them. But we are, so it's time to bring the big data back onto the blockchain. So that's, TrueBit is taking this piece right here, computation, and that's what we're bringing onto the blockchain. So, and there's also a communication component to it. Just like you have the internet for big data, we're looking at something like Doge Ethereum Bridge, a way of bringing existing bridge, take the tokens off Dogecoin and put them on Ethereum and back. So that's the functionality we're talking about here. So TrueBit is a scalability solution. And in terms of the storage piece, so I'm talking about TrueBit as a scalability solution for computation. But if you look at the storage situation, there are a lot of projects already looking in that space already. Most of them are more focused on privacy than data availability, but there is interesting things going on in the storage department. In fact, there's interesting stuff going on everywhere. I guess that's why we're here. But what is it about TrueBit? What are we here to talk about today is a process which we call interactive verification. Okay, and what is, what are we focused on? TrueBit is focused on large transactions. So we've had a few talks just recently about sharding. So TrueBit is not going to assume that you can take your transaction set and break it up into smaller pieces. You have a massive transaction that's coming in, and you have to process it. So that's what TrueBit is all about. Okay, so what's the problem? Well, what are we trying to solve here? I guess I don't really have to tell this audience what a smart contract is, but I do want to point out a sort of critical property of the smart contract is that they only, this sign at the bottom, which you can see now, says small computations only. You're not running computations that run for hours or even minutes. I mean, they don't even run for seconds. So that's what we mean by scalability. Computations that actually run. So the length of the computation you can run is bounded by Ethereum's gas limit. So the obvious thing, let's get the elephant out of the room. Why don't we just dump the gas limit? So first, so what is the gas limit? Ethereum meters smart contract storage and compute resources with a measurement they call gas. And the gas limit is the maximum amount of gas that you can allow per block. It's not per transaction, it's per block. And so why do we have the gas limit? That's a question. So reason A, is it because every miner has to replicate every Ethereum computation? B, it's because removing the gas limit would leave Ethereum vulnerable to denial of service attacks. Is it C, because the gas limit helps incentivize transaction verification? Or is it just that Vitalik Buterin secretly doesn't want Ethereum to scale? Well, I think we can quickly cross out D because it's not a secret anymore. I told this same joke a few weeks ago at CESC. So now what I do want to do is convince you that C is, well, I say all of these answers are true, but C is more true than all the others. So this is what I want to convince you in the next 3 slides, that C is actually the right answer to this question. So let's see what happens without the gas limit. Okay, so no gas limit. You have a guy with 2 pointy horns comes in with a heavy transaction. He incentivizes it nicely, so someone is bound to pick it up. You put a nice big transaction fee. So a miner comes in, mines the block. He says, sure, I'll include that because he's got an incentive for it. And what do the rest of the miners do? They just get like completely confused, right? Because why are they confused? So let's look at a little bit into their confusion. So what are they confused about? So this is actually a principle which we call the verifier's dilemma. So in the case of a heavy transaction, what should a rational miner do? Rational miner being somebody who likes to earn more ether. So number 1, skipping verification affords an advantage in the mining race. So therefore, he has a reason to skip the verification. Mining on the wrong chain, on the other hand, means that other miners will ignore the found block. So therefore, you should skip the verification. So it should be clear from looking at these 2 statements that rationality doesn't actually help you decide what to do. So the miners want to do whatever other miners are doing. So that's the verifier's dilemma. So what is TrueBit? TrueBit is a solution to this verifier's dilemma. It sort of makes it so we put everything off chain, so you don't actually have to deal with heavy transactions on chain. What we've sort of observed in blockchains, and this is kind of the miracle of the whole thing, is that miners are willing to do a small amount of work for free, and then you don't have a verifier's dilemma. So here with TrueBit, we are going to give Ethereum a computational boost by doing the heavy work off-chain. So the goals of the protocol is that anyone can offer a reward for performing a computational task. Anyone can solve a task in exchange for a reward. The protocol, most importantly, guarantees correctness of solutions. And here by anyone, I mean anyone. That means a smart contract, pseudonymous identity, or the bots that came up in the earlier talk this afternoon. And so if you want to say formally, what is TrueBit? It's an Ethereum smart contract. That's one part of it. But it's also a new off-chain architecture. So I'm going to walk us through these 2 pieces in the remaining time. So let me try to explain let's look at the architecture piece first, just as an overview. So TrueBit is a unanimous consensus algorithm. Unlike Ethereum, which you sort of have majority vote on the miners, people say like this, anyone in TrueBit can challenge a computation by taking it to court, so to speak. And who sits in the court? Well, it's your miners from the Ethereum network are sitting in this court. They're always right, but they have very limited computational bandwidth. As we just see, because of the gas limit, because of the verifier's dilemma, you're stuck with that. So what can we do? So you have a solver who comes in did a computation, and then a challenger who comes in and says, well, you're wrong. And the solver doesn't actually say, let's play a verification game. He gets forced to play a verification game. He gets taken to court. Okay? So what does the court do? It tries to pinpoint the place where they're disagreeing. So you have a solver and the challenger, they enumerate their computation states. They do all this off-chain. And then the judges are going to enforce a binary search to find the first step in the computation where they disagree. So solver says, here, he kicks out his, obviously they agreed on the green means they agreed. So they agreed on the first step because that's the input, it's just given. And they didn't agree on the end, or they wouldn't have been in the court in the first place. So he says, do you agree halfway through? Challenger says, no, I don't agree on that. So we mark that as red. Do you agree at step n/4? Says, yeah, okay, agree at step n/4. What about 3n/8? So we're just getting, now we're there, these are close enough. You can actually run this one step of the computation. You can do it on chain because it's small. And it's important to note here that the computational steps have to be absolutely identical across all the platforms in order to rule fairly on the final check, right? There's no notion of one step if everybody's running a different set of steps. So the judges, we have to make sure that that's the key property of our architecture, is that all the steps are exactly the same. Okay, so what happens here? So here was the last step where they agreed, and here's the step where they disagreed. This step was of course provided by the solver. So he's saying, so I'm talking about this. This is a picture of a Merkle tree because you can sort of, to optimize space on the blockchain, we represent these states in form of a Merkle tree. But you can think of it as a Turing machine. So you said you have a machine. It's in state Q0. It sees a 1. So then the program, he's claiming that the program says write a 0, change to state Q1, and move to the left. If you don't know what a Turing machine is, that's fine. Just note that whatever the judge said, he noticed that it did something different than what the solver claimed it would. So it's the solver is wrong, so the challenge is justified, and that forfeit is now deposited. Forfeited. The deposit is forfeited. So now let's look at the other piece, the smart contract piece, which is sort of the crypto-economic innovation part of this project. So how do you actually ensure that this verification actually occurs, right? What if nobody shows up to take you to court? Then it doesn't really work. So how do you make sure that people actually use the court the way it's supposed to be used? So the second idea, you offer rewards for checking computations. Just pay everybody for who checks. So now how do you know that they checked? Well, you go back and run the computation yourself. You check that they checked. Well, you might as well have just done the thing yourself in the first place. So this incentivizes participation if you pay people, but it doesn't incentivize correctness. So idea 3 would be that you offer rewards for finding bugs. So this gives you correctness, but it doesn't incentivize participation when there are no bugs. So it's the opposite problem. So essentially, we have the problem that these verifiers stop paying attention if they don't expect to receive any rewards. Okay, this brings us to our final scalability idea for this talk, which we call forced errors. And that is that we're going to offer a bug bounty and provide expectation that bugs will. And so this is actually what TrueBit does. Occasionally, the protocol pays solvers for submitting incorrect solutions. You have to get it wrong. So the dispute resolution ensures correctness whenever forced errors are not in effect. What do I mean by that? Since you're only having maybe 1 out of 1,000 times you might have a forced error, but the idea is that every verifier doesn't know when the forced error is going to come, so they're just going to check everything. So most of the time, the verifiers think they're getting paid, and the solver thinks someone's going to watch, and therefore he gives the right answer. And ideally, if we made our compiler exactly right on this architecture, no one's ever going to go to court. This subroutine is never even going to be executed. So that's a lot of work for code that you're never going to run. Now, if you only remember one slide from my talk, please look at this one. This is a picture of an illustration of Simon de Rouvière's panoptic computer, which is based on Bentham's panopticon, and which has physical manifestations in the state penitentiary in Joliet, Illinois, the Presidio Modelo in Isla de Pinos in Cuba, and it's a prison, okay? So you have, in the middle, there's a watchtower with someone who's looking around into all of these cells. There's a bright light, so they can't see what he's looking at, But out of fear that the guard sitting in the watchtower is actually looking at them, they actually behave correctly. So that's the principle of the panoptic computer. It's all about, you imagine that these people sitting up here are all performing the computations, and they do it correctly because they think they're being watched. So, and I just quote from Michael Foucault, who is also an important figure he wrote a book, in the 1970s about panopticism. We have seen that anyone may come and exercise in the central tower the functions of surveillance. So anybody can sit in there. Now, there's no reputation. This is exactly an illustration of TrueBit, because there's no reputation in TrueBit. Anyone can come in and do that. So let me, in the last few minutes, talk about the developments that we're going on with TrueBit right now. So the TrueBit virtual machine, when I speak of the virtual machine, I mean specifically this new architecture that's offside, which is part off-chain, but also your on-chain stepper, which allows judges to participate in this mechanism. So as I mentioned before, the tasks have to compile and execute identically on all machines. Otherwise, there's no notion of step, and the judges can't really participate. So they all have to be the same. The other thing is that your single computation step on the TVM has to be running within Ethereum's gas limit itself. So into this, and you also have to, the space required to describe a state change also has to fit inside Ethereum transaction. So ideally you'd use a Turing machine, as I said before, but there's no, at least I haven't found any code that takes a bit of C code and turns it into a Turing machine. So we had to do the next best thing, which is go to WebAssembly, and we even broke that down further. We have each WebAssembly step is broken down into basically 16 sub-steps, sort of. So we have these properties of our architecture. So if you look at what does it look like overall, the picture of the TVM. So you have your C and C++ code, and it's coming in to you want to run this task. So your smart contract needs some computational boost. So you have a C or C++ code that says the task that it wants performed, and it wants to ensure that it's done correctly. You can use this property called an unscriptin, which we use to transform the C++ code into the WebAssembly code. Now that WebAssembly code is used in two places. It's used both off-chain. We use the OCaml reference interpreter to generate the states, your list of computation steps that are going to go through on the computation. That's used by the solvers and the verifiers. Meanwhile, the task giver pitches this WASM task actually he commits the task to the chain itself so that it's enforceable, so the judges can do it there. And then all of this stuff about the incentives that we discussed before and the forced errors are monitored there, and we have this is what holds the money that pays out some of the incentives. And here's where the judges live. They're running, that's on-chain, and it runs one step. Now I want to point out that we do have a new file system for TrueBit, which basically has, it currently has two flavors. One is, even if you store the data on the chain, you still need a file system to access it on the blockchain. So you can put your data on the chain, and the advantage there is that it stays there. But the disadvantage is you can't put very much. IPFS, on the other hand, you can store whatever you want, but data availability, well, ideally we want a system that has both of these properties. The data is available and you can put stuff there. So to be continued. So let me just wrap things up. We're in the process of one of the first applications of TrueBit is going to be the Doge Ethereum bridge, and we've got the code ready on the Ethereum side, but we need to reach out to the Dogecoin community and get them to put in the new opcode that we need, which is going to be something that allows people to take Dogecoin off the Dogecoin network and put it lock it on the Dogecoin side, unlock it on Ethereum, use it in a smart contract, whatever, and then lock and unlock, send it back, it's a Doge again. And in order to reach out to people, we are instituting a new public art project. So I'm calling everyone who's interested in being part of this amazing movement. This is a once-in-a-lifetime opportunity. Come talk to me after this talk. As I mentioned earlier, we're live on Kovan testnet. And all of our code is up on GitHub. Check us out on TrueBit. Follow us on Reddit, Medium, GitHub, Twitter. and Facebook. And thanks, everybody.
Okay.
Thank you very much, Jason. Next up, we have Joseph Poon, Scaling Ethereum Smart Contracts.
Where do I go? Do I watch there? I'm okay. Hi, everyone. Can I do this with no slides? Oh, I have slides. That's fantastic. I'm probably going to be looking this way because that's the only view I have. Oh, that's loud. Hi, everyone. I'm Joseph Poon. I'm here to talk about Plasma, and this is going to be sort of an overview for about the first 10 minutes. So if you've already seen the other presentation, a little bit of this might be review. So the second half is going to be sort of exploring the narratives around data availability and the data availability problem. Vitalik has been talking about this data availability problem for the past several years and is very critical when it comes to Ethereum base layer scalability, such as sharding. Today I'm going to be talking about the implications of data availability when it comes to building transactions when we're talking about Plasma in particular. So Plasma is a project that right now is being architected, and after that will be written, and it's co-authored by me and Vitalik, and hopefully, a lot of people in the Ethereum community can contribute because I think this can be, a lot of fun. So Plasma at its core is about building a blockchain on top of a blockchain. So you write the smart contract inside Ethereum, and you initialize it by basically taking a library and modifying it to whatever particular use you need. So for example, you can build some social network, some decentralized exchange, or even some private blockchain. I think the private blockchain example is pretty interesting because you can build a private system with your own rules, with your own participants, with whatever terms you want, but also enforceable on the public network. That's pretty effective because right now a lot of private blockchain systems are role-playing, right? A lot of the systems they're building today can be modified by the operators of these systems. If it's these 5 people, then you're sort of like, well, all my money is sort of at the whim of these 5 people. If you bond your activity in a private chain to a public network, that allows everybody in the world to sort of say, okay, this allows the Ethereum network to sort of be this base layer for all of these private chains interacting in the future. And that could be an interesting aspect to develop on. And the way this works is that in the smart contract, you make it so that the consensus rules are defined inside Ethereum itself, where you upload the smart contract, and it's enforceable via fraud proofs. And each individual Plasma chain has its own consensus mechanisms defined inside the smart contract, and it could be written in Solidity or in the future, more likely Viper. And the goal is to build decentralized applications at scale where you can create, like billions of transactions per second is sort of the goal. Given certain security constraints. The presumption is that you're not really trusting them, and the way you do that is that, let's say you're Alice, you have 1 ETH held inside this Plasma chain, and this Plasma block periodically commit block hashes onto Ethereum. So it's very, very small, measured in hundreds of bytes, and which can encompass perhaps gigabytes of data. This is not proof of existence. Proof of existence is another form of like role-playing that people use when it comes to building blockchains inside blockchains. This is actually enforceable. The notion is if you create an invalid block, if a block is invalid, it can be penalized and rolled back. And what this allows you to do is allows you to create a lot of transactions inside a system. This is, of course, assuming data availability, and data availability is an interesting problem that we'll get into in greater detail later. And essentially, this is an example if someone submits an incorrect transaction, an incorrect block rather, and then what happens is someone submits a proof onto Ethereum, and you submit a Merkleized proof. And it's actually very similar to the previous presentation about TrueBit, where you have Merkleized enforcement and Merkleized attestation. And by having Merkleized attestation, you can represent information in a very, very compact way. So for example, if this very, very specific, let's say 100 bytes within a block inside this plasma block is invalid, you just say, okay, these 100 bytes are invalid, here's a proof that these 100 bytes were inside this plasma block, and then you submit that inside Ethereum, and it's very, very compact. That allows you to say, okay, one piece of this entire block is broken, let's roll it all back. And then in that moment, the individuals that created that block get penalized, and that allows some measure of honesty when it comes to propagation. But the core notion of Plasma is not around the notion of Merkleization of information. The core notion is about exiting in the event of data unavailability. Data unavailability is an interesting problem because you can't prove when someone is withholding data. It's sort of like if Alice says, oh, I gave the data to Bob, and Bob says, no, Alice didn't give it to me. Who do you know is right? You really can't, beyond like having this trusted third party, and in Ethereum we try to like reduce that as much as possible. And what you can do in Plasma, and this core of Plasma's construction, is this allows you to exit in the event blocks are withheld. So Plasma blocks in this case. So it's saying that if let's say block number 4 is committed, so this 100+ bytes is committed onto Ethereum, and it's like, wait, I don't have this data. I can't prove this as false. I can't prove that it's invalid. So then what you do is you then submit it, and then when you not submit it, you exit, and basically you exit from that chain. Because you're like, well, someone's not giving me the data, there could be bad data in there could be bad state transitions. It's sort of like if a party starts sucking, you just leave. You don't try to make, it's like a party's a disaster. You're just like, well, you can try to make it better, but you could just leave and join another party, and it's much more fun that way for everybody. And the fun part is when you do blockchains and blockchains, you could do blockchains and blockchains and blockchains and blockchains, and that gives you even greater scalability where you could do like potentially billions at this point, representing a single use case, for example, like fun posting in some live chat. You could do that and like, build a system where you could, make that enforceable in some way. And that gives you a great deal of computational scaling. This is not just computational scaling of financial activity, but potential anything. This could be a system where, you move from, centralized data services with, like Reddit or Twitter or whatever it may be, and you can credibly decentralize this since capacity is significantly increased to an incredible degree. This also lets you do computation using MapReduce. So you go like, okay, map, and you map out all the blockchains and blockchains. They do computation across many, many different blockchains, and you reduce the results back down. It's sort of like returning variables. So you just have one way of splitting up the work and one way of returning the work, and that's sort of how you reach incredible computational scale. So the design goals is, one blockchain can encompass, all worldwide computation. Maybe not all as in everything, but all as in like, there's no necessary constraints given the security properties of the system. And the goal is to do trust minimization where you're not trusting the people operating these Plasma chains, because you can ultimately go to Ethereum and enforce invalid state transitions. And the goal is to payment and ledger scalability. Ledger scalability is interesting because ultimately you want records, and it's sort of like state channels gets you like, an X percent, X times scalability. This can give you, many, many X, and Ethereum sharding can give you many, many other X's, and then at that point you can reach incredible scale. And I believe that, this is very much in the near future, measured in, very short time frames, not like 10 years plus, but closer to like low digits in amount of years. But transaction data I think can give you an example of the problems that we're dealing with. This may be a little bit, more architecture. So if you're a little bit, it may be a little bit hairy. This requires some knowledge in the way, atomicity works. But basically what we're talking about is that, you want to create a transaction, and you want it, and then let's say you just broadcast it inside this Plasma block. You're done, right? Not really. you can't attest to this payment if the block is being withheld. Remember, like that block number 4 I was going over earlier? If that happens, then if you make a payment, you don't really know if that payment is in there, and like you don't know if the correct amount is in there. You don't know if like the current state is correct. It's just being withheld from you, and you can't even prove that it's invalid. It's sort of like all you can do is just say, well, maybe my payment is in there, maybe it isn't in there, or maybe it's wrong. And if it is in there and you try to withdraw an old state, then you get penalized. If you try to withdraw and it isn't in there, well, then that makes no sense. That won't work. And if it's incorrect, well, you have a big problem, right? And normally when an incorrect state is attested to, you just exit. But in this case, you may not have enough information to exit. So that's sort of a problem that needs to be addressed within the context of data availability. And you're not sure if those funds are spent even further, right? Maybe that transaction went in to this plasma block, and maybe later it gets withheld because it gets spent. A separate transaction spends it. So that could be a big problem. This problem also exists when you put funds into a plasma block as well. So how do you address this? You address this by creating this two-phase commit process. This is a very different way to do it. This is not a hard necessity for a lot of problems, but if you want 100% certainty, this is sort of how you would do it in the event of data withholding. We don't have this problem on the Ethereum base chain, right? On Ethereum, all you do is you just broadcast a transaction, it gets confirmed, you're done. The reason it's not a problem in Ethereum is because it has presumptions of everybody having the data available. Ethereum works by I receive blocks, I don't trust anyone else, right? Anyone else on this network, and when I receive it, I compute it, I validate it, and I just make sure that it's true according to the consensus rules on my computer. And what happens is I can process the current state, but you could also do a full replay of the entire blockchain history in order to have 100% assurance. That's not necessary, but you're capable of doing that because you have the data available. In this case, when you split up into all these different plasma blocks that are only committing very small pieces of data onto the Ethereum main chain, what happens is that in this plasma block, there could be information you don't know about. And this, when someone's withholding, you can exit. But what happens if you don't have all the data? So in this case, what you do is you create and broadcast the transaction, much like you do normally. And in this case, the plasma block gets signed by a validator, so it gets included into a plasma block. And then step 3 is where it gets weird. Alice commits that she saw her transaction get submitted into a block, and she can give that to Bob, or she can submit it onto the plasma chain so that there's like a second record. So it's sort of like I submit a transaction, and I submit another transaction saying I saw the first one. And then at that point, when Bob sees that second step, whether it be directly from Alice or from the plasma chain, Bob now has assurance that the money is his. Why do we do this, right? Alice needs to be sure that the transaction has occurred, and she's able to reference it. Remember that Merkleized proof stuff? So Alice now is able to reference that transaction existed, and now Alice is able to be assured of it, and now she's willing to attest that, okay, this money is no longer mine. And this is sort of the one weird trick to make this all work. And as Bob, you're only willing to accept the funds when you receive that second step, because at that point, Alice cannot claim the funds according to the consensus rules written in Solidity or Viper on the base chain, on Ethereum, basically. It says like, okay, once the second signature happens, Alice no longer has any claim to the funds. And essentially, we're dealing with 3 parties here: Alice, Bob, and the plasma chain itself. So let's go over these 4 steps. There's Alice, there's Bob, this is the chain. And that's sort of the state, so that's the third thing I was talking about. Alice has 1 ETH, the plasma chain is there, and then Ethereum on the base layer, which periodically gets commitments and exits and deposits. So Alice signs a payment. So this is like very similar to how Ethereum works. You just send a payment into the plasma chain. Ultimately, the plasma chain creates a block, and then it sends a commitment onto Ethereum, and it says, hey, I made a block. Here's a couple hundred bytes. Alice and Bob then get the data of that plasma block, and it says, like, okay, I see this block is legit. Okay, there is a payment going on. Alice and Bob both see that there has been a payment from Alice to Bob. Notice on the top right, it shows Alice or Bob, because either Alice or Bob can claim this according to the chain itself. Step 3. This gets a little bit tricky, but it'll make sense. So Alice then submits a commitment signed by herself that she has seen that previous transaction, and essentially she's able to prove it because she sort of like can see the data there and sees the Merkleized commitments. So she's like, okay, cool. This money's no longer mine. She passes it off into the plasma chain and Bob. And now, from her perspective, it's not her money anymore. If she tries to claim it, that's bad news for her because she's not able to do that or gets penalized. For Bob, it's sort of like, well, okay, if he hasn't received it yet, oh, there's a slide skipped. Oh, well, anyway. So for Bob, let's say Bob hasn't seen it yet. That should be a dash. Then Bob doesn't yet know whether it's Alice's or Bob's. From his perspective, it should be Alice's. And for the chain, it sees it as Bob's because it received that transactions and confirmed. In this case now, that should be a dash line to Bob, not dash, solid line to Bob, so we're correct here now. Bob now sees the funds as his because he has that commitment and the original transaction. So Alice now has no claim, and in the top right, you now see Bob has the 1 ETH. So creating this two-phase construction allows Bob to know that Alice no longer has any claim to the funds, and Alice has assurance that she does not, she will have the funds available if the block is withheld at any point in time. So as an example, let's say Alice tries to maliciously withdraw the funds. If Alice tries to withdraw the funds during step 3, what happens is that when it's not fully committed to Bob yet, she submits a transaction onto the Ethereum main chain, the Ethereum root chain, i.e., basically what we call Ethereum today. And let's say the holding period is 14 days before she can correctly withdraw, and she has to put up a bond. Assume that Bob believes that the money is his, because he has the information available to prove that Alice has committed to the fact that she saw her original transaction. Then what Bob can do is take that proof that says Alice says, hey, I saw this transaction hit the block. Here's a proof that this transaction hit the block. And here's a commitment that I have submitted this transaction. Bob should say, okay, that money is mine now. But if Alice tries to take that money, Bob can submit to Ethereum that says, okay, Alice tried to submit this. Bob sees it on the blockchain. And he says, okay, Alice screwed up or is trying to take my money. Here's a proof because Alice gave it to me and I saw it on the chain. And now what happens is Bob is even happier because she takes her bond and it's his money back. So this type of construction, by constructing a two-phase commit process, you're basically making attestation on information availability. And this is going to be, I believe, an emerging theme when you're dealing with states where not everybody in the world has information, right? We're not dealing with global state anymore. How do we deal with this, right? In channels, the way we deal with it is we can only move forward if both parties have it available. But we're dealing with perhaps thousands of parties, billions of parties maybe eventually. And different people will have different sets of data. So, the goal is to be able to make it so that you can have attestation correctly and to scale, perhaps, the blockchain can be the ultimate arbiter. In this case, Ethereum can basically be the Supreme Court of computation across the world. Thank you.
That's great. Thank you, Joseph. Next up, we have Jakob Eberhardt. His talk is Socrates, a toolbox for ZK snarks on Ethereum. Jakob?
Hello, everyone. Let's see the slides first. Hi, so my name is Jakob Eberhardt, and I work at the Information Systems Engineering Group at TU Berlin in Germany. And I'm here today to talk about Socrates, which is a toolbox for CK snarks on Ethereum. So let's first look at how transaction processing works in traditional blockchain networks. As you can see on the left, the transaction is sent to the network. That then gets validated at the first node and is then broadcast to the other nodes. And at some point, it gets included into some block after someone solved the proof of work problem. Now imagine if we had a system like on the right side, where a transaction is sent to the nodes in the network, but instead of directly being validated on-chain, they get forwarded to a third party, the yellow box here, and that's where the transaction processing happens. After the processing off-chain is done, the result is written back to the blockchain, and on-chain, it is verified to be correct. Only that verification would then happen redundantly and not the transaction processing itself. So what would be gained through that? One thing would be scalability. If the verification is cheaper than redoing or executing the transaction in the first place, if you only have to do the verification on-chain, then you can increase throughput. Also, there is no such thing as a block gas limit that comes into play here because there's no need to circumvent the halting problem. A second aspect is that private information that gets used on that external node can, if we use the right tools, be kept private, and they do not have to be published to the blockchain network, which is also what we not have at the moment. So what are approaches for that? We've heard an excellent talk by Jason earlier about TrueBit, and TrueBit is one such approach where you gain scalability by off-chain computations, and then there's that verification game played on-chain, and with that you gain scalability. Another approach is non-interactive zero-knowledge proofs. In that case, you additionally have zero knowledge. That means the private information you use during your processing on that external node, they are not revealed to the network. Okay, so what could those non-interactive zero knowledge proofs be? One proven mechanism is CK snarks. I think many of you are aware of that technology, and it stands for zero knowledge, succinct, non-interactive arguments of knowledge. And here are several key properties of CK snarks. So the proofs are short and non-interactive. That essentially means you can simply take a proof generated by a prover, send it over the network to a verifier, and without further communication, it can then be verified. Also, we have a zero knowledge property. That means some information that goes into the processing is not revealed to the network later on. Verification cost, and that's a big one, is independent of the computational complexity of the initial computation. So no matter how complex your computation is, the cost of verifying a proof is always the same. Okay, so that's a key aspect. Now, a little inconvenience is that to specify computations in a way that you can do zero knowledge proofs on, you have to think in an abstraction that's not very convenient to most developers. So, for example, you can specify computations as arithmetic circuits or rank 1 constraint systems. Of course, you can do it, but it's just not convenient to do, and that's what impacts usability negatively. Let's take a brief look at the process of using CK snarks before we move on to the tool itself, because it's necessary background. So here on the left, we have a circuit or a rank 1 constraint system that encodes a computation. In that case, we just multiply two numbers and demand that that equals another number. And for example, RSA encryption uses a similar construction. From that circuit or rank 1 constraint system, the first step is the so-called setup phase, which is needed to arrive at the proving key and a verification key that are then later on needed in the proving process. So this setup has to be performed once for a circuit or a rank 1 constraint system, and then it can be reused over and over again. On the right side here, you see the verification process. Based on that proving key, a prover could, for example, first find the solution for the problem at hand, and then generate a proof that it correctly executed that computation and found a solution. And the cool thing is, it could optionally supply all the information that went into the processing, but it could also keep some of the information to itself. In that example here, the prover only supplies set, which is the result of the multiplication, and not the factors themselves that went into it. And the verifier can then check the correctness of the computation without redoing it. And that is much cheaper, that verification process, than the proving process, and with that the execution of the computation itself in the first place. Socrates. So with Byzantium, Ethereum added 3 new precompiles that enable CK-SNARK verification on-chain. So we have elliptic curve addition, scalar multiplication, and a so-called pairing check. But the big question is, how do we use that? And that's where Socrates comes in. So the vision of this toolbox is to provide a usable abstraction and tooling to support CK-SNARKs on Ethereum, to actually make them usable. The goal is to support the complete process from program code specification to on-chain verification of the execution of that program code. It's supposed to seamlessly integrate with Ethereum, that we'll see in a minute. Socrates comprises several things. One is a domain-specific high-level language that allows you to specify your computation in a more abstract way than arithmetic circuits or rank 1 constraint systems, which are inconvenient. Then we have a compiler which transforms these programs into provable constraint systems. And then there's support for the different phases we need to go through with CK-SNARK. So the setup phase, finding a solution to our constraint system, which is the witness computation, the proof generation itself, and then we can also, using the tool, export a Solidity smart contract that can then be used to verify the computation on-chain. Let's briefly look at the language. So the language at this point is pretty close to the constraint system, but provides some more convenient abstractions to specify circuits. So the data type we have is prime field elements. You can just think of these as positive numbers smaller than a huge prime number. So essentially think of it as positive numbers. Then we have imperative statements, which is the abstraction most of you should be used to when programming. We have assertions, we have loops, we have conditionals, and we have functions which allow you to structure your code and keep it a bit less redundant. So let's look at an example here for n choose k, or a binomial coefficient. The upper function here computes the factorial. We'll not look at that in detail because it's just not important. What's more interesting here is the lower part, it's the main function. As you can see, the main function here takes 2 arguments, n and k, and then there's a return statement. Now in Socrates, the arguments of the main function and the value of the return statement are public. That means when you prove that computation, you use that code to prove the correct execution of that code, n, k, and the return value become public. If you do not want that to happen, if you want to keep that private, that information, you can simply not list that as arguments, but still use the variables in the processing, as we do here. And then, when you supply the proof and the inputs, n and k do not appear in there, and all the person verifying that thing would know is that you computed the binomial coefficient and what the result was, but n and k would not be known. Let's look at the user perspective and the command line interface Socrates provides you. So you start with high-level code, you write that high-level code, and it gets compiled to a set of conditions, or also called flattened code. Based on that, you can then find a valid variable assignment for that code, which is basically a solution to your program. And that's called a witness. So you can use a tool to find solutions for your programs, and it also supports you with a setup phase. So you can use a tool to compute a verification key and a proving key, which you will need later on. Based on the verification key, you can derive a Solidity smart contract deployed to the network and then verify proofs that were generated with the proving key that came out of the same setup phase. And to generate a proof, there is that generate proof command, which takes a given witness that you computed previously and the proving key, and together you generate a proof that can then be verified by the smart contract you created beforehand. The internal architecture of the tool looks like this. So we start with code in that domain-specific language, and that goes into a parser, is then flattened, and then you have an interpreter which computes solution to the program. Here you can decide which part of the solution will become publicly available and which part will remain private. So here you have the control, and then after that we do just some format conversions to interface with the libsnark library, which we use for the ck-snark operations themselves. Then there's the contract exporter, which can be used to export Solidity smart contracts to verify proofs. Okay, the on-chain proof verification looks like this. So on the left side here, we have what the Socrates tool generated is a proof. It consists of 8 elliptic curve points and inputs. On the other side, we have a verification contract, which we also generated, and that contains a verification key. 7 elliptic curve points is what that is made up of. And then there's the verify function, which uses the new precompiles that came with Byzantium to check the validity of the proof and also make sure that the inputs were correct. At the moment, a verification like that costs around about 1.6 million gas, so actually a lot. That means on a Robson testnet, we can do 4 in one block. On the mainnet, it's currently 6 in one block. The gas cost varies a bit with the amount of input parameters we give with the proof, but the main cost is constant and rather high. A couple of challenges and outlook of how we want to proceed with Socrates, what would be cool in the future. So I think for the language to be more usable, more convenient, we would want additional types. So for example, Boolean types. Everything you can do with Boolean types can be done now, but it's just not as convenient to do it on prime field elements. And then some integers that have a binary representation internally. What's very important, and that's basically implementation work ahead of us, is a domain-specific library with important functions. So next thing we need, in my opinion, is a hash function, so we can do commitments in circuits and then signature encryption. That would be nice to have. Also, we want to look at integration of other front ends that can also be used to arrive at rank 1 constraint systems, for example, Buffett. A generic ck-snark challenge that is not specific to Socrates, but rather, always comes up when speaking about ck-snark is the trusted setup phase. So if you supply a verification smart contract and you want to verify something someone else proves to you, and you're the only one to be convinced, you don't have any problem. You run the setup and you know that you did it correctly, and thus you can trust the proofs, and you know that the person proving to you cannot fake proofs because you were in control of the setup. But if you want to use these proofs to also convince third parties, other parties observing these proofs on the blockchain, then they would have to trust you with the setup phase. So what would be great if we could eliminate some of that trust by integrating a distributed setup phase. It just would have to become a bit more efficient than it was in the Zcash multi-party computation protocol, for example, which they employed to do their setup. So I think we'll hear more about that on Friday in the CK Snark breakout session, hopefully. Okay, so the code is open source. It's available on GitHub. You're all welcome to try it out. I'm happy to receive your feedback. Keep in mind it's a proof of concept and a research prototype at this place. We're actively developing it, and we're always happy for people who want to contribute to the further development. You can also contact me by email, and I want to give credits to Christian Reitwiesner, who always provided very valuable feedback and input in discussions, and also to Dennis Kunert, who contributed a lot to the existing implementation. Thank you very much.
Not yet, Vitalik. Jared's gonna introduce you, so just wait a second. Just wait a second. Devcon3 Universal Sponsor Status, a quick greeting and introduction by Jared Hope.
Hi, yeah, I'm Jared from Status. I still remember the day that Vitalik published the Ethereum white paper and captivated us all with the idea of a programmable blockchain. And here we are, like 3 years on, and he and other scientists are still furthering blockchain technology in ways that I haven't even imagined. But a lot of this research doesn't really mean that much without all the hundreds of contributors from the community who help build and maintain this public infrastructure. And basically, if you are interested in contributing to Plasma, Viper, Whisper, Swarm, PSS, Viper, please find me and talk to me, because I would love to chat with you. Thank you very much, and here's the chief scientist himself, Vitalik Buterin.
Okay, great. So I was originally here to give a talk specifically about what was called maximally verifying like clients and sharding, and I will end up touching on a lot of that in this talk in certain ways, but I also wanted to make it broader a bit and basically make it be not just about scalability and just about sharding, but also a kind of general outline at a proposal for what I think a sensible path for Ethereum protocol development in general to be going forward over maybe the next 2 to 4 years or so, right? So I'll start off by just let's take a look at what's been going on in Ethereum so far, right? So in Ethereum, we've first of all had a lot of successes. So first of all, the Ethereum blockchain and the Ethereum protocol work. You may have noted the total lack of a crippling DDoS attack on the network this year. Many applications, and we've gone to somewhere over 1,000 applications at this point, and I'm pretty sure people aren't even really counting anymore. And it shows in all the charts, right? So this is the Ethereum transaction chart, and we just recently broke above 500,000 transactions per day for the first time, which, in case you can't divide, is something like over 7 transactions per second. And so it's or almost exactly 7 transactions per second at the peak, actually. So the amount of activity on the Ethereum blockchain is orders of magnitudes higher than it was 1 or 2 years ago. And this includes not just Ether transfers, it includes ERC20s, it includes Ether Delta, it includes various different dApps, it includes just a whole bunch of different smart contracts of various types. This is another diagram I'm fairly proud of. This is the global Ethereum network with more than 20,000 nodes worldwide, with hubs existing all over North America, including East Coast and West Coast, hubs all over Europe, a bunch in Russia, a smaller but still very significant and growing amount scattered across the various hubs in Asia, and increasingly nodes starting to show up in places like South America and Africa as well. According to the data that got scraped from either this site or another site a couple of days ago, we seem to have 1 node in North Korea, but not sure if that's actually in North Korea. Yeah, so in general, a lot of progress, right? And if you look at just Byzantium as well, the Byzantium hard fork basically, has gone through, and you can now take advantage of cryptographic primitives that are available in an accelerated form on top of the Ethereum blockchain in order to build privacy-preserving applications. And people already are. So, you just saw Socrates in the last presentation. Just yesterday, I saw on Reddit someone announced a protocol that was doing a reputation market based on ZK snarks. There's I know of one project that's trying to do things with ring signatures, actually multiple projects. So I also know of at least a couple of projects that are taking advantage of RSA verification to do things like better communicate between Ethereum and existing DNS, between custodian e-residency and just various other things. So the privacy part of the 3 kind of major challenges to Ethereum's success that I've outlined, privacy, security, and scalability, is actually quite well on the way to being solved. Now, there is still a lot of work to be done. Someone actually has to build the ring signature stuff. Someone actually has to build Socrates. People actually have to use it. People have to actually make using zero-knowledge proofs practical. But we've made progress. So what are the challenges? So scalability is probably challenge number 1, right? So this is a quick excerpt from the sharding FAQ where I talk about this challenge called the scalability trilemma. And I basically state that it seems likely that blockchain systems can only have at most 2 of these 3 properties at the same time. Number 1, decentralization, which I define as basically being able to run without trusting supernodes, scalability, so being able to process many more transactions than a regular laptop, and security, so basically, it's okay to be vulnerable to 51% attacks, but you definitely cannot be vulnerable to 0.51% attacks. There is a very, very big and growing graveyard of systems that claim to solve the scalability triangle, but actually completely don't. So, I actually think that the scalability triangle is solvable, but it basically requires significantly more kind of complex technologies than, the kinds of technologies that we have available. Part of this is something called the data availability problem, which I'm not going to talk about today because it really does require a 1-hour presentation to go through. But basically, it's this problem that a lot of people don't even think about, but basically, not only do you need to verify that the blockchain is valid, you also need to verify that everyone can access the blockchain. And even ZK snarks and starks cannot solve that part of the puzzle. And there's mathematical proofs based on information theory that say that if you cannot solve that part of the puzzle, your protocol is basically cannot be secure. The relevant paper here is basically one that says that batch updates for cryptographic accumulators are impossible. And so hat tip to Justin Drake for that one. So it is a very significant and hard challenge. So basically right now, every node processes every transaction. The capacity of a blockchain is limited to the capacity of one node. And it's actually even worse because we need to have safety margins for anti-DDoS purposes. The limiting factor in Ethereum scalability and Ethereum's likely worst point of DDoS vulnerability is likely to be disk reads. And also Ethereum VM execution is currently absolutely not parallelizable. So, these are just known facts, and they severely limit the extent to which Ethereum in its present form can scale. So, the likely solution to a lot of this, now there are more incremental solutions that we can do. So, for example, you can use EIP 648 to greatly improve parallelizability. But if you want to really solve the fundamental problem, every node processes every transaction, basically sharding. And the way that you think about sharding is, well, basically you can split the blockchain state. So split the set of information that everyone needs to keep track of into n universes, and we call each one of these universes a shard, right? So each universe has its own account space, its own accounts, its own contracts. You can have transactions within each shard, and you only allow asynchronous communication between shards. So if you want to send a coin from shard A to shard B, you actually have to have two transactions, the first transaction on shard A and the second transaction on shard B. And contracts on shard A cannot synchronously call contracts on shard B. So you cannot call a contract on shard B and get a response and do something with that response in one transaction. And the benefit of this is that each client only processes a small portion of all the activity on the network. So the reason why we call it quadratic sharding is because if you imagine, the processing capacity of one computer to be n, then you can imagine n shards, and each shard has, like n worth of activity. Each node would have to process the activity on basically just the one shard it's interested in, and every node would have to process the activity of kind of the entire system of shards. So the amount of activity of each node would basically be n at the top and n at the bottom, so a total of 2n, but the capacity of the entire system would be n squared. And theoretically, you can make the sharding be exponential, but quadratic is simpler, and there might be good reasons to keep it quadratic. And it may well be, say, we only do sharding up to quadratic, and if you want to go up to exponential, then basically you have to stick with things like sharding in Plasma, or sorry, state channels in Plasma. Another challenge that we've had is this kind of challenge of governance and protocol evolution. So basically, we have this trade-off where, on the one hand, we want progress, but on the other hand, there is demand for protocol stability. And hard forks making deep changes are hard. Right, so we finally gotten Byzantium out on October 16th, and Byzantium is the result of over a year of work, a large amount of testing, and even after a year of testing, we still required some pretty epic work between the Go team and the Parity team doing super advanced forms of fuzz testing that I don't even fully understand in order to catch a fairly large number of bugs that appeared pretty close to launch. So hard forks making deep changes take a long time to code, take a long time to agree on, a long time to test, and there is a high risk of consensus bugs, especially since the Ethereum network has basically 7 different clients that that all have to implement the protocol and agree on it. But even still, even with all these challenges, we've done Byzantium and we've done it successfully. So. But the problem is, right, that on the one hand, hard forks making deep changes are hard. On the other hand, to get to what we want to see in Ethereum, to get to this kind of highly sharded, highly scalable network, as well as all of the EVM upgrades we want to do, all of the parallelizability upgrades we want to do, EVM 1.5, EWASM, potentially more precompiles, in order to get to this ideal end state, very deep changes are exactly what we need. So what do? How do we handle the trade-off? So intuition, one blockchain, two systems. And I'll make this clearer with the kind of diagram that I'll show in the next slide. So here is what a sharding system, as we're already starting to build, could possibly look like, right? So you have the main chain. And in the main chain, it's basically, everything is basically as it was before. You have your blocks, you have your state root, you have your transaction root, you have your state, you have your your accounts, your contracts, your storage. Now, what we're going to do is, in the main chain, we're going to add something called a validator manager contract. Now, what does the validator manager contract do? It basically runs a proof of stake system that maintains the consensus for a kind of two-layer sharding system that exists kind of on top of or even inside the main chain in a certain sense. So the validator manager contract would keep track of validators and would allow anyone to join and leave the system, serve as a validator, and basically assign the right to create blocks on in each of these N shards that the validator manager contract keeps track of. The VMC would also keep track of block headers for each of these shards, but what the VMC would not do is it would not verify the full blocks of the shard, and the VMC would not contain a copy of all the new consensus rules. Instead, basically, actually creating valid blocks, actually enforcing that the blocks are valid in the shards, actually enforcing that the data in the shards is entirely available and follows the desired consensus rules, basically would be the responsibility of the proof of stake that exists inside the validator manager contract. So the validator manager contract would initially be this kind of very low risk thing to participate in. There would actually not even be a risk of total slashing in the same way that there is in Casper. And the goal would be to basically just get, like a fairly significant portion of Ether stake participating in this, and basically, if you are part of the validator manager contract, then you just get assigned randomly the right to create blocks in each and every one of these shards at periodic intervals. I should probably use more correct terminology. We call the blocks inside of shards collations. So if you have a transaction, then transactions get grouped into collations, and the collation headers then get put into the validator manager contract, and they get put into transactions that get included into blocks. So we have this kind of two-layer structure where at the top layer you would have the blockchain, and at the bottom layer you would have all of these different shards, and each shard would be like its own universe. And connecting the two universes, you have this validator manager contract, which enforces the proof of stake, basically maintains a built-in internal light client for each of the shards, and processes and facilitates things like, like moving Ether from the main chain to the shards, and possibly from one shard to the other. So you can think of the kind of differences between, like the two systems, between the main shard world and the new shard world, so somewhat like this, right? So scalability, so main shard is OFC, so C is the letter I normally use to refer to the computational capacity of one node. So the main shard would have a scalability of just OFC, which is exactly what it does now. And the new shards would have a capacity of OFC squared. And the reason for this is you have OFC shards, and each of the OFC shards itself has OFC capacity, right? So, by the way, if you're not familiar with big O notation, just don't think about the O's. Main chain scalability of C, new shard scalability of C squared, because there's C shards and each shard has C transactions per block. Consensus algorithm. So on the main shard, the consensus algorithm is currently proof of work. In the very short to medium term, we hope to transition it into hybrid proof of stake in the form of a Casper friendly finality gadget, a paper for which was released on Archive something like 5 days ago, and which is actually, I would say, nearing the kind of final stages of full specification. And eventually, we would transition the main chain consensus into full proof of stake. Now, the consensus switch itself is designed to be fairly conservative, and so possible to implement in this kind of fairly slow and careful way, right? So for example, the first part of the switch to hybrid proof of stake actually doesn't require a hard fork. Technically, it does. I mean, it requires this weird kind of soft fork where basically it's not even like a real soft fork. Instead, it's just an optional change to the fork choice rule that's used inside of a client. The only thing you would need a hard fork for is when we want to basically stop providing rewards to proof of work miners, or at least reduce the rewards to proof of work miners and switch the rewards to validators. So the switch to proof of stake, I'm fairly confident, can be done in this kind of gradual, fairly conservative way. Main shard has full security, basically the same security guarantees we can expect to have now. And the governance of the main shard basically, in order to kind of satisfy the demand of people that really wants to have, like, basically stronger immutability and less risk on the main chain, we can, we can have norms of governance that emphasize conservatism and strong immutability more than today. Now, what happens in the new shards? So scalability, OFC squared. Consensus is this proof of stake, where in order to vote in the proof of stake, you would have to deposit Ether into the validator manager contract, and the validator manager contract would randomly assign to you the right to create blocks on all of these shards. The security would be 50% honest majority of the on-chain proof of stake holders now, and basically once the what we want to do with Ethereum 2.0 and sharding solidify enough, then eventually the shards would be kind of tightly coupled, and the two would have roughly the same level of security. And now the governance for the new shards is basically just going to be on-chain Ether voting, right? So basically, for these new shards, because you have this proof of stake, we might as well have this proof of stake be used in order to basically vote on what the protocol changes are within this sharded universe, right? So basically, validators themselves already are going to be the ones that enforce the consensus rules. So, why not just have them be, just the one? They kind of are the ones that decide on the rules already. So we might as well accept this, and we basically actually take advantage of this because this kind of on-chain ETH voting governance would give us the ability to basically emphasize fast evolution in the new shards initially. And then when we have this tight coupling, and when every client becomes basically a fully validating client for all the shards, then the kind of governance would become much more conservative. So this is kind of the dichotomy that I'm suggesting, where we can have these two universes at the same time, where the universe on the left, the main shard, is just basically continues working as Ethereum. We do not need to negotiate EVM 1.5, negotiate EWASM between 7 different Ethereum implementations. And we can focus on relatively milder things that do things like state size control, that do things like just improving security, possibly improving parallelizability a bit, heavy focus on the proof of stake switch. And we have this other new universe, or really these new N universes, in which basically the implementation of all of these things that we've already been working on over the last 1 to 2 years can basically be rolled out onto the mainnet much, much faster. So here's what an implementation roadmap might look like, right? So sharding road, basically step 1 is you would implement this kind of sharding universe as a proof of stake sidechain. And in a proof of stake sidechain, in each shard you would have collations, and the collation headers would be verified and processed by this on main chain validator manager contract. Block creation rights are assigned by a simple proof of stake in the VMC. Clients would just get randomly assigned the right to create blocks and randomly shuffled between shards. And in the first step, you could have one-way ETH convertibility. In the second stage, you could make the ETH convertibility two-way. Now, this is what a node for the Ethereum sharded network might look like, right? So you already have the existing Ethereum nodes that talk to the existing Ethereum network. Everything on the left does not need to be changed one single bit. What you have on the right is you could have a sharded chain node. Sharded chain nodes would be responsible for basically broadcasting full collations, right? So collation headers would go into the validator manager contract. Full collations would only be broadcasted in this sharded chain network between all of the nodes that are participating in the sharding system. So sharded chain node would be written in Python initially, and it could be designed in such a way that it can talk to any Ethereum node by RPC. Now, if we want fast evolution, we could have basically 1 or 2 clients for the sharded chain node initially, and then over time, ramp it up to the full 7 as more teams become ready. So, basically, you would have this kind of fairly, kind of partial split between what happens on the Ethereum side and what happens in these sharded networks, where basically you would really have a shard network for basically every single shard, right? So after this, you would add two-way convertibility. You would move the collation headers from the VMC into, let's say, being main chain Ethereum uncles. And then step 4 would be tight coupling. So tight coupling basically means if you have a block in the main chain that contains a collation header which is invalid, then the entire main chain block is invalid. So invalidity on the shard side will be able to cause invalidity on the main chain side. And this would be basically when the main chain and the shards would both switch into this kind of tighter security mode. And stage 4 is something that theoretically could happen later. Ideally, it should happen basically when things on the sharding side are actually reasonably stabilized. So remember, the shards that I'm suggesting are creating new address space. They are not affecting existing address space. This gives us a unique opportunity to make many very important, many efficiency improving, but backwards incompatible changes to the Ethereum protocol. So what kind of changes do we want to make? Well, we can just list through a few, right? So number 1, changing Merkle trees from hexary trees. This is a no-brainer. It makes the Merkle proofs 4 times shorter. Account state tree redesigns. So you might want to get rid of contract storage trees. You might want to have like multi-level nested trees. You might want to have a different account system. These are things that we can brainstorm. These are things that we can think about and optimize. EVM upgrades. So basically, can we make the EVM efficient enough that pre-compiles are no longer necessary? It seems like it's very likely that we can. So in the Ethereum community, we have had these kind of 2 paths for optimizing the EVM, where one of them is this kind of Greg Colvin's approach of EVM 1.5, which is more moderate upgrades and additions to the existing EVM. And the second one is this kind of full-scale replacement with EWASM. Well, basically, the idea would be let's work together, let's come up with what combination of these 2 models seems most reasonable, and let's just immediately apply it as the only EVM available in the shards. And so this way, you would have much more efficiency without having to worry about as many backwards compatibility issues. Parallelizability. So there are fairly simple Ethereum upgrades that we can do. So EIP 648 is one example. There's also a sharding EIP, which is a stricter version of EIP 648, which basically lets you execute Ethereum transactions in parallel. If you can do that, then we basically have, if we want it, kind of unlimited access to the kind of big block scaling route, right? So if we have parallelizability, if we want to, we could always make the blocks bigger, and all that would happen is that the kind of resource requirements of running a node would just be a bit higher, but if you have enough cores, you would still be able to process a block fairly quickly. So parallelizability is something that if we tried to add it to the existing Ethereum, it would require some fairly deep changes, but if we can make this kind of new system where we have parallelizability right from the start, then it might be easier. Stateless clients. So stateless clients are a topic that I've read, but they're a topic that you might end up hearing about more and more over the next while or so. The basic idea behind a stateless client is this, right? So, as you might have seen from the diagram, stateless clients have something to do with a Merkle tree. Everyone bow down to Ralph Merkle again. Yeah. Okay. So, consensus nodes do not hold the entire state, right? So consensus nodes, so basically full nodes, miners, anyone, do not need to hold the entire state. They only need to hold the root hash of the state. People who want to send transactions would apply attached Merkle branches, so witnesses, basically proving the correctness of the specific portions of the state they want to access. So if you have a state root, and if I want to send a transaction that sends 10 coins from address A to address B, I would provide 2 Merkle branches that prove the existing balances of address A and address B. Then the transaction, the blocks would get passed around with the witness, and that's all the information that a node needs in order to execute the block, execute every transaction in the block, and figure out what the new state root is going to be, and what the new Merkle branches are, and what the portions of the state are that got modified by that transaction. So the idea here is that we can substitute each individual instance of a disk read. So basically, each individual instance of reading a storage key or an account from disk, which takes, possibly something like a millisecond, with about 1 kilobyte of bandwidth, assuming we optimize the Merkle tree and assuming 1 billion accounts. If we go up to 1 trillion accounts, then we'll only need SHA-core 1,300 bytes of bandwidth. Now, the benefits of this are that, first of all, it makes it much easier to reshuffle validators when sharding. Basically, the idea is that if you're in a stateless client architecture and use get suddenly reassigns to a new shard, you do not have to download the state of the shard. In a stateless client paradigm, fast syncing is literally pretty much instant. And this is true regardless of what the state size is. Stateless clients allow us to care much less about the state size. So even if the state was, like 1 petabyte, nobody really needs to store that 1 petabyte. And they massively increase parallelizability kind of as a side effect. So, like this is one other kind of secondary scalability path that, basically it might even just make sense to do it in the sharded universe from day one. So, regardless of kind of each individual proposal, right? The general idea is that, we could have ongoing development of the Ethereum protocol happen in 2 layers, where the first layer basically involves relatively small chintzy improvements, getting Casper rolled out, and then the second layer is the one where rapid development and experimentation happens, and it's the one where, we could get to thousands of transactions per second actually fairly quickly and on a significantly accelerated schedule if we want to. So if there are applications that do not need super duper high security, then they can just go on layer 2 fairly quickly. So this gives us the benefits of basically both approaches at the same time, right? So safe and conservative layer 1 and all this rapid development in layer 2 and the ability to use layer 2 in order to do all of these protocol improvements that developers have been dreaming about the whole time without having to go through this kind of political process of getting all 7 clients to agree on it and write a million tests for it and fuzz it for 6 months in the short term. In the longer term, even as the sharding system solidifies, of course the sharding system will end up focusing more and more on conservatism and security, and eventually the two will be kind of merged in some nice and clean way. But this is something that if we want to, can wait 3 or 4 years. So the good news is that along with the initial work on sharding proceeding very quickly to the point where we are basically just inches away from having a working Casper proof of concept testnet in Python. We also have initial work on sharding that's being done in this repo. So, we have some developers that are working on a sharding capable client. And that are starting to work on some of these stateless client improvements, starting to experiment with some of these optimizations. And the hope would be to also, if there are other client developers that wants to participate in this as well, then this is something that should happen totally openly, and this is a process that should eventually go beyond just happening inside of one client. And basically, in the short term, the sharding stuff would continue as kind of proof of concept in test mode. And the nice thing is that because this is not being done as a hard fork, because this is being rolled in gradually as this kind of loosely coupled overlay at first and tightly coupled over time, basically there is no sharp testnet to mainnet cutoff, right? So the extent to which the shards are a testnet and the extent to which the shards are a mainnet actually kind of flows fluidly from one to the other over time. So, basically this way we can get development of both scalability and a large number of other needed improvements in both quickly and safely with respect to the existing Ethereum protocol. Thank you. Thank you.
Thank you all for coming. And together with our community and attending developers, I believe we've made the best Devcon.
sequence numbers are enough. There's no, the sequence numbers are enough. Hey. Oh, to what? Oh, okay.
Can I ask the panelists to please take their seats? Vitalik, Vlad, take your seat. Peter, Goon, yes, please.
Well, where's the mic? Can you use this? Oh, that's pretty far. Can I have another handheld mic?
Test.
Okay, all right. Hello. Okay, and we are moving on to the panel, and this panel is about Casper and distributed consensus. My name is ゚D㚚щ. I'm a professor at Cornell, and I'm very honored to moderate this panel. We have 4 distinguished panelists, and I'm going to begin by having the panelists each spend 2 minutes to introduce, and also maybe a short, concise statement or pitch that you would like to make regarding distributed consensus. And then I'm going to ask questions, and I'm going to open it up for the audience to ask questions. So because we have a big room, for those of you who want to ask questions, I'm going to ask you to move to the front so everyone can hear you when you ask questions. Okay, all right. Let's maybe start from Vitalik. Okay.
Okay. Hello everyone. Who here does not know my name? Okay, I see some hands raised. Good. I'm Vitalik, Chief Scientist of the Ethereum Foundation. So earlier this morning, I gave an introduction to basically what Ethereum is from a technical standpoint, but I also mentioned that later today I'd be talking a bit more about some of the projected things that we want to do in the future of Ethereum. And one of the big threads kind of research and developments that we have at the Ethereum Foundation is Casper. So Casper is this kind of category of proof-of-stake consensus protocols that we have been thinking about and developing, researching over the last... Looking at Bitcoin, people were excited about Bitcoin, but people were also realizing that blockchains are useful for things other than just money. So back in 2011, there was a project called Namecoin, which was trying to make a blockchain-based domain name system. In 2013, there were projects called Colored Coins, which were trying to digitize arbitrary digital assets or arbitrary assets and put them on the blockchain. There were protocols called Mastercoin that were trying to integrate all sorts of fairly complex features. So there was a consensus that you can do lots of different really cool things with Bitcoin or with other blockchains. Asset issuance, crowdfunding, title registration, lots and lots of stuff. Problem is, most blockchain protocols were designed like this. Pocket calculator, single purpose device, works reasonably well for all you care about is adding and multiplying numbers, but it does nothing else. And sure, someone with an advanced computer science degree with a good calculator can kind of hack it to play a video game inside of it, but do you really want to do that? So after this, in 2013, there were people who were making protocols that looked like this. So Swiss Army knife. Basically, you come up with a list of 10 or 20 features he wants to have, make a little tiny thing for each one of them, stick them together into a knife, and there you go, that's your product. Or in this case, that's your blockchain. So back at the end of 2013, there were lots of projects that looked like this. They just said, okay, we want blockchains to be usable for asset issuance, crowdfunding, bets, prediction markets, identity registration, title registration. Pick a list of 20 different things, have a list of 20 different transaction types, and have a little piece of the protocol that supports each one. So this is all well and good, Problem is, what if you come up with your list of 20 applications, publish a protocol, then the next day some guy says, oh look, I discovered a 21st blockchain application. How am I going to fit it in? And in 2013, this is exactly what started to happen. So this is the Ethereum way. So why do we love smartphones so much? Basically because a smartphone is nice and generic. You buy it once, and download immediately comes with 50 or 100 applications. If someone comes up with a new application, they write the code, they upload it to the Google App Play Store, and if you want it to be accessible in China, you can upload it to the Huawei store as well. And then if anyone wants to use your application, they don't need to buy a new phone, they don't need to buy a new hardware dongle. You just download the app and they can start immediately running it. Very simple. And the cost of actually developing an application, all you have to do is write code. You don't have to make your own hardware, you don't have to have your own manufacturing, you don't have to have your own distribution. Just write a piece of code, upload it, and let people download it, and you're done. So this is the kind of abstraction and simplicity that I wanted to bring to the blockchain world with Ethereum. So Ethereum is a blockchain. I'm sure if people here are familiar with blocks, I'm sure people here are familiar with transactions. And these are all well and good, but Bitcoin has them too. Namecoin has them too, Litecoin has them too, Dogecoin has them. I'm not sure if Paycoin has blocks though. I don't know, Paycoin might even run on a server, I haven't even checked. Proof of server, the best kind of POS. But we have a few tiny additions. So the main thing that makes Ethereum tick is this built-in programming language. So basic concept is, if you have some new kind of application, then what you would do is you would write the rules of your application in a piece of code. Take this piece of code, you would call this a contract, upload it to the blockchain, and now you have a special type of account. And this type of account sits on the blockchain, and anyone can send a transaction to this account in order to interact with this account. So two types of account. One type of account is a user account, controlled by people like you. And the other type of account is a contract, which is controlled by a piece of code. If you send 1 unit of Ether to an account that is controlled by code, then no person controls it anymore. The only thing that can actually move that Ether is the execution of that contract's code itself. So it basically is an automaton sitting on the blockchain that's executing exactly as the code on the blockchain says it's going to execute. So this is all well and good. Let's try an example. So the hello world of Ethereum is sort of basic, a minimal sort of DNS system. So the idea here is you want to store a mapping of basically domains. So you have something like I don't know, Vitalik.eth, George.eth, Ethereum.eth. Ask me about my cool Ethereum hacking services.eth. So you have a bunch of domains that people might want to register, and for each one you want to store the IP address that it points to, and you want to store who owns that domain at that particular time. So we have two functions. One of them is for registering a domain, and the logic is pretty obvious. If the domain has not yet been registered, then you set the owner to yourself. And another function that says set the IP address. If you own a domain, then you can set the IP address. And this is like basically the minimal thing that's like all you need in order to have like a maximally simple domain name system. Now, as I understand, Nick Johnson is going to be presenting about a kind of much more complete and better one at some point over the next 3 days, but this is sort of the kernel. This is what you start with. So you have this piece of code. Then what you would do is you would compile it. You would get some bytecode, then include the code in a transaction, push the transaction up onto the blockchain. Now what you have created is a contract. And a contract has an address. It has some 20-byte string that represents sort of the location of the contract. It will look like 0x357c, whatever. If you want to register a domain, what you would do is you would send a transaction, and you would specify this transaction is going to be talking to this contract. Now, what can the transaction do? Well, it can try to register, or it can try to set the IP address. So let's say you want to register a domain. What you would do is, in the transaction, you would encode some information that says, I want to call the register function, and I want to call the register function with like some particular piece of data. like, I don't know, George.eth or whatever. Take this transaction, include this data, publish the transaction. When the transaction gets included, the code runs, and you notice it says self.domains address.owner equals msg.sender. So what that line of code basically does is it says, whatever address sent that transaction, record that address in the contract storage as the owner of that particular domain. So you notice at the top of the contract here, it says like data domain, so it basically stores a mapping going from a domain to the owner and the IP address of each domain. So the code and the storage, like both of these things are what we call sort of part of the Ethereum state. So what we mean by the state is sort of current information associated with the Ethereum protocol. So stuff that you have to care about right now. This includes account balances, how much Ether you have, nonces, it includes contract code, and it includes contract storage. So for example, right now, this piece of code is nowhere in the state. If I send a transaction, publish a transaction which creates the contract's code is now in the state. Now, if I send another transaction, which then talks to this contract and registers a domain, then the process of executing that transaction is going to change the state. And the new state is going to contain some storage keys that basically say this particular domain has some particular owner and some particular IP address. So that's kind of what the state means. So it's stuff that you have to kind of care about now. So in Bitcoin, for example, the state is pretty simple. It's just like how much money everyone has at some particular point in time. The second thing is history. So history is things that happened. So transactions are part of the history, receipts are part of the history. Don't have time to go into them, but feel free to research them more. So this is kind of important because a lot of people ask things like, oh, you know, who stores like the transactions, or if a contract executes, then like who executes the contract, so like where are the results stored? And like the answer at this point basically is that if you are a full node, then as a full node, what you do is, number one, you download all the blocks, you download all the transactions. When you receive a block, what you would do is you would see what the state was before the block, then you would execute all the transactions in turn, and you would update your own state. So all full nodes basically execute all transactions, they would execute all contracts, and full nodes, some of them store the history, some of them don't store the history. So like there are clients that are increasingly coming out that let you sort of not store large portions of the history, and this is good because it saves you hard drive space. So the state in Ethereum consists of basically a key value mapping. So basically the state in Ethereum is like a bunch of account objects. And account objects, once again, two types of accounts. One of them is just an account controlled by a person or some external user or controlled by a